Okay, so we are now on the second part of the module on distillation, and this is the second set of slides. Now, the first one was focused on the use of the graphical technique in determining the number of stages for our distilling column. Now, it also gave you the introduction to distillation and the necessary material balance equations that you will be using. Now, for this afternoon, we will start with the analytical process of determining the number of stages. Though it's analytical, you still need to refer to graphs that are available in your handbook or the equivalent of such graph that is available in Gian Cookleys. Okay? Now, when you want to determine the number of stages for your distilling column, analytically, meaning you're going to refer to a graph, but this time you are not going to anymore draw the operating lines. You still have to start with the concept of the minimum number of stages, the minimum reflux ratio, and aside from that, you're going to determine the theta because it's needed in the formula. So I have placed in here the steps that you will determine, that way you can be able to solve based on a formula the number of theoretical stages for your column. Now, the first formula, this is available in Gian Cookleys, has the variables Q, the alpha, the X, and the very important theta. Now, since this is summation and since our distillation is limited only to binary systems, that is, we only have two components in our feed, then expect that in the right side here, you will have two rational expressions, two fractions, that is, one fraction that will represent A and one fraction that will represent B. So if it's A, this will be alpha A, X sub A, F. F here means feed, alpha A, and this is your theta. Now the second term will be alpha B, X sub, or X with the subscript BF. This is also alpha B minus theta. And as such, since you have two fractions, it will be a trial and error procedure on determining the value of theta in the two fractions that you have on the right side. That way, if you sum up the two fractions, it will be equivalent to 1 minus Q. So in the same manner that Q is very important in the graphical technique when you draw your feed line and determine correspondingly the intersection of your feed line or your Q line with the enriching section operating line, it is also very important in here because you need it in the first step. So once this one is wrong, once the Q is wrong, everything that you'll be doing will be useless because it's dependent on this first step that you did. Okay, so determine first the Q and determine the alpha. Now, what is this alpha? I'd like to go to the next page first, then I'll go back to the steps that we have there. For those who have already read Gian Cookleys, the alpha, if you have a two-component system, will be the alpha of the components of your system. So alpha A will be equal to K sub A over K sub B, and alpha B will be equal to K sub B over K sub B. When we choose alpha class, or when we determine the alpha for a binary system, we choose among the two components that we have, which one will we use as a basis in determining the alpha for the two components. So if you choose B, it follows that your alpha B would be equal to 1 because you have this particular formula. If it's choosing A as the K sub A, then this would be the one that would be equal to 1, and this one will have another value. Now, again, if you've read your Gian Cookleys, this K is the distribution coefficient or the equilibrium constant for your system. Now, where do you get it? Now, Gian Cookleys gives this a very simple graph of where you're going to get the K based on the temperature of the system. So, kung ano nga temperature ang ginhatag sa imo nga system, then that would be your basis in here. So, you have here the K on the vertical axis, and you have here the components of your system. So, in this case, you have, let me check if it it would be okay to have this projected. I hope you can still see it so that it would be bigger. You have here butane, you have here pentane, hexane, and heptane. So given the temperature, you go up, you look for the appropriate curve, and then read on the vertical axis on the left the corresponding value for the K of that particular component. Let's say, for example, you have a butane-pentane system. So if it's a butane-pentane system and you chose butane as A and pentane is B, automatically your alpha B will be 1. Your alpha A will be the K of butane for the specified temperature, and the B will be that of pentane. So you just read here the corresponding value of K sub B, and in case of butane, that would be K sub A in here. Okay? Check the equivalent of this equilibrium K values in your Paris handbook because it's the one that you're going to use. Okay, I just took this one because this one has only 4 and it's easier to have it pasted in here. Okay, so this is how you get the alpha. Now, what will you do with this alpha? I'd like to go back to our slide. Now, what would you do with the alpha? I'll try to project again. So that alpha should be multiplied to the mole fraction in the feed of that particular component. So you determine the mole fraction of A in the feed, you multiply it with alpha A. The denominator will be alpha A minus theta. Of course, theta is unknown. For the second term in here on the right side, you will have alpha B, which is 1, times X sub B in the feed, or the mole fraction of your B in the feed divided by, again, alpha, which is 1 minus theta. So you do trial and error in here. I think it's easier with your calculators now because all you have to do is place the equation there and substitute value for theta. That will make the value that you have here on the right side nearest to, if not equal to, 1 minus q. Of course, you know already the q. Now, what are you going to get from here? You're going to get here the theta. The theta that you have in here will be used in determining the minimum reflux ratio. Now, in graphical technique, this minimum reflux ratio is solved using the pinch point coordinates, if you could still remember, the x prime and the y prime. But since you will not be using graphical technique when you do it already in the licensure exam, so you should have an alternative equation to use. So this is this alternative equation. Having known already the theta from step 1 in here, you determine this R sub m using this summation again. So you will still have here alpha, but this time in the numerator, instead of multiplying your alpha, whatever that alpha is, alpha A or alpha B, with the mole fraction in the feed, this time you're going to multiply it with the mole fraction in the distillate. The mole fraction of A in the distillate divided by, again, alpha A minus the theta that you got here, plus you should have another fraction in here, and that should be your alpha B x sub B D, the mole fraction of B in the distillate divided by alpha B minus theta. In the process, you'll be getting the R sub M. So I have included in here the section in Gen Please where you can read this particular procedure of determining the R sub M. Now, what's the purpose of determining the R sub M? Now, I'll leave this page here, and we can go back now to the original graph that I have shown to you the previous meeting. Now, in this page, in this slide, in our PowerPoint, I hope you could see, you have in the curves the value of the minimum reflux ratio divided by that same reflux ratio, minimum reflux ratio plus 1. So you're going to determine the value of this and look for the appropriate curve. If it's not amongst the curve that is specified in here, you can approximate. So let's say, for example, you have 0.35, so it must be somewhere this 0.3 and this 0.4, so that this is your 0.35. If it's 0.38, so you'll have somewhere in between 0.35 and 0.40, and so on and so forth. Now, the reflux ratio, most of the time, is, excuse me, class. So most of the time, the problem class gives you the reflux ratio R. So you can solve for the value of that. So using these two, you'll be getting from the horizontal axis the ratio of the minimum number of stages and the theoretical number of stages. So this N sub M is the minimum number of stages, and this N is the theoretical number of stages. Now this N sub N, oftentimes, so that it would be simpler, you will not be doing a lot of things, you will just solve this using the Finsky's equation. And Finsky's equation is dependent on the mole fractions and the uh, geometric mean, the geometric mean of the volatilities of your distillate and your bottom's liquid. Now, as to how to determine the minimum number of stages using Finsky's equation, that will be discussed in the sample problem after this one. That way, I will not have to repeat. But you have to determine the minimum number of stages. That way, from the value that you have here on the horizontal axis, you'll be able to get the theoretical number of stages. Okay, so that's it, class. So you have to follow, excuse me, you have to follow a three-step procedure in determining the theoretical number of stages. What I have here placed in number 3 is an alternative of how you're going to find the R sub M using the X prime and the Y prime. That is, if it's just easy for you to plot your feed line. Actually, it's easy to plot the feed line and then correspondingly have it intersect the equilibrium curve that you have. The problem with this class, if you don't have the equilibrium data, that will make you graph the curve, the equilibrium curve, which is actually a product of plotting the XY pair of data for your system. The mole fraction in the liquid and the mole fraction in the vapor of, let's say, component A in your system. So that's what you're going to use. That way you can come up with a curve. So if you don't have that, and if you don't have a ready-made equilibrium curve for your system, then do the procedure that is written in here. You determine your R sub M using this particular formula. Now, if you did determine the X prime and the Y prime using graphical, since you already have the curve, let's say for example, you have it already in the book, or you have a reference wherein you have a curve beside you to use, then you can determine the minimum number of stages there. All you need to have is the XD and the XW. If you recall our discussion last meeting, all you have to do is start making steps from the XT down until you reach X sub W. You don't need the operating lines to simply make your steps touch the equilibrium curve. Again, that is if you have the equilibrium curve. So we forget about that if we don't have the curve, we don't have the data. So we have to rely totally to formulas and this figure by Urbar Maddox, which has also an equivalent in your handbook given by Gilliland. Now, in here you have the R and the R sub M needed. That way you can get the value of the ratio of N sub N to N. Now, after that, you need to determine the minimum reflux ratio. That way you get to know the theoretical number of stages. So far, that's the procedure of having to determine the theoretical number of stages here analytically using the formula and the curve. Do you have any question for now?
Yes.
Yes, you have any question?
None, yes.
Okay. Sige, just wait. Give me just 10 seconds. Now we will continue here on the determination of the feed plate location. You can only answer this using this equation by Kirkbride if you know already the theoretical number of stages. So meaning you are to determine first the n here from this figure together with the minimum number of stages. That way you can use this particular equation. Now, what do we have in here? So in here you have the log of the ratio of the number of stages in the enriching section to the stripping section number of stages. The H and the L that you see here in the formula means the higher boiling point component. This one is the lower boiling point component. The F here means it's in the feed. So you are to get the mole fraction of the high boiling point component in the feed and the mole fraction of the low boiling point component in the feed. Now, how do you know whether A is high boiling point component or B is low boiling point component in the feed? If I may ask you, what tells you that A is low boiling point component and B is high boiling point component? Let's say you have benzene toluene system. Now, which of the two will be your high boiling point component, which you will place in here, the mole fraction in the feed, and which one is the low boiling point component? What is it that tells you in your system that this one is low boiling point component, this one is high boiling point component? That way you can place here properly the mole fractions. Because if you interchange the two, it follows that your equation here, of course, you will have a value that is erroneous. So what tells you that one is low boiling point and one is high boiling point? You can write on the chat box, class. Fritz, are you there, Fritz? Dekaniel, Fritz. Oh, I haven't. Okay, so what tells you that a component is the low boiling point component or the high boiling point component in your system? How do you tell which is which? Because you need to choose. You need to choose what value you need to place here in the mole fraction. Do you have any idea? Fritz, you may write your answer. Wala gid idea. How about a guess? Give me a guess. Let's say benzene toluene. Which of the two is low boiling point component and high boiling point component? So one answer here is you refer to the volatility. What if you want to save time? Of course, that's true. You can refer to the volatilities. You go back to section 2 in your handbook. You check which of the two has a lesser volatility. Then that's the low boiling point component. Now, how do you know that it's the low boiling point component and the high boiling point component? Mole fraction. Okay, there are two answers here regarding mole fractions. We don't use the temperature as a basis because they are at the same temperature because they belong to the same system, benzene and toluene. So you are right, Vincent and Drexel. You are to refer to the mole fractions. So let's say you have a system which is 40% benzene, 60% toluene. Which of the two is the low boiling point component? Which one is the high boiling point component? Any guess? Or I'll go back to you, Fritz. I have a benzene toluene system, 40% benzene, 60% toluene by mole. Which of the two is the low boiling point component? If you're given a benzene toluene system, Fritz, benzene is 40% and toluene is 60%. Mole percent, that is. Which of the two is the low boiling point component? Bia answered benzene. What about the rest? You can write your answer on the chat box. Which of the two will be the low boiling point component? Benzene. Benzene. Okay, I like the answer of John Vincent. Benzene, since it has the lower mole fraction. So that's how you tell which of your components in your system is the low boiling point component. The one that is present in the least amount in terms of mole, that's the low boiling point component. I'm referring and I'm talking about the feed composition. So the one that is present in the least amount is the low boiling point component. You can check that further by referring to section 2 of your handbook regarding volatilities at the given temperature of the feed. Then you would know which of the two components is more volatile. Okay, it's very important, class, that I'm asking that. It's because your formula here needs you to identify which one is the high boiling point component and the low boiling point component. The same is true with what you have in the distillate. Anyways, if you have identified already that benzene is the low boiling point component in your system, in the distillate, it's also the low boiling point component. You don't base it on the, rather the mole fraction, because we know that the component that goes to the that is converted into the distillate, you only have two, let's say benzene and toluene, is the most volatile because what you have in the distillate is the lower boiling point component, or the lowest, the one that has the lower boiling point. Okay, so it's important in here, in the formula. You have here the amounts. So this W and the D refers to the amounts of the bottom's liquid and the distillate. This one will give you the ratio of the number of stages in the enriching section and in the stripping section. So once you have already the theoretical number of stages, that NE plus NS should be equal to the N theoretical. So from your answer here on the right side, you will have something to equate the ratio, or that is the ln, or the log of the ratio of n sub E and n sub S. If you will express one in terms of another, you'll be able to solve for NE, for example, or NS. Okay, so if you assign, for example, NE, let's say your theoretical number of stages computed is 12. So we say that NS is equal to 12 minus N sub E. You substitute it in here, you'll be able to solve for the number of stages in the enriching section. Let's say, for example, the number of stages in the enriching section is 5. How would you be able to tell the location of the feed plate? Because this formula primarily is used in determining the location of the feed plate. How will you know? Let's say you already determined that the enriching section has 5 number of stages. How will you know the feed plate location based on this number of stages in the enriching section? You can write your answer on the chat box. This is already your enriching section, number of stages. And I have already introduced to you the graphical way of determining the number of stages and the feed plate location. Even with this just one information, you'll be able to answer the feed plate location. How will you answer the feed plate location? It was also discussed in the first half of this module. If you have 5 for the enriching section enriching section number of stages, then where is the feed plate located? Or what stage will you introduce the feed in your column? 7. Some more answers? What's the feed plate location? Do you think what would be our feed plate location? Isa, Ramos, Isa Ramos, are you with us? What do you think will be our feed plate location if the enriching section has already 5 stages? Isa Ramos, are you with us? Six. Okay, that's correct. So your feed plate or your feed will be introduced on the 6th plate from the top of the column. Why is that? If you've been carefully listening and if you have been intent on listening on the discussion in the determination of the number of stages graphically, uh, if you have noticed, the feed plate is where you have the transfer from the enriching section to the sleeping section. The very first opportunity that you get to transfer from the enriching section to the sleeping section, passing the intersection point of the 3 operating lines: enriching section operating line, sleeping section operating line, and the feed line. So, and then I've mentioned that your feed plate is always part of the stripping section. It's part of the stripping section. So if you have already determined that your enriching section has 5 theoretical stages, isn't it that the 6th would be part of the stripping section already? So that first plate from after the enriching section belonging to the stripping section would be now the feed plate location. So if your enriching section has 5 theoretical number of stages, then the feed plate will be located on the 6th stage. Or shall I say, your feed will be introduced on the 6th stage from the top of your column. Okay, that's the purpose of having this ratio of the number of stages in the enriching section and in the stripping section. Do you have any questions? Clarifications? Do you have any questions? I think there's none, so we will proceed. Okay, we'll go to the sample problem that I have placed in here. This will give light on how you determine the minimum number of stages using Finsky's equation or Finsky's method. Okay, so this is our sample problem number 2, focused on the analytical way of determining the theoretical number of stages. Okay, let me just check because it's not projecting. Okay. I hope you could see it. So your system in here is pentane and hexane. You are given a 40% pentane, 60% hexane feed. Now it is saturated liquid with a flow rate of 2,500 pound-mole per hour. Your column is operating at 1 atmosphere. Now your distillate has 90% pentane as desired. Now, a total condenser is used. So, meaning all vapors that is living on top of your column is condensed by your condenser. Reflux is a saturated liquid. So, your vapor condensed into liquid is returned in part into the column in the form of reflux liquid. Now, your bottoms from the reboiler is 90 mole percent and hexane. Okay, bottoms from the reboiler. So now it has more hexane and distillate has more pentane. So from here, you get to check, validate that your less, the component pentane which is present in the least amount in your feed is your low boiling point component because it's the one that goes into your distillate. The high boiling point component remains as bottoms liquid. Now determine the minimum number of equilibrium trace and the minimum reflux ratio. In here, you are to determine the minimum reflux ratio, so that would be the R sub M, and the minimum number of trace, that would be the N sub M. So the procedure that will be done in here, you can apply in the analytical way of determining the theoretical number of stages. Now, excuse me, class. Now, what's the minimum number of equilibrium trace? So if you're going to plot a given, let's say a given pair of X and Y value for your system, the minimum number of stages, as I have mentioned, this is the third time already, will only require the mole fraction of the least boiling point component in the distillate and in the bottoms liquid. And then you start off drawing your steps from these two, from the XD down to the XW. Now, it's presented in here that this is the data of the pair of X and Y. So good if your problem has this because you can do graphical. But if you're not provided, you have to do analytical. So in this case, we'll just do graphical. That way you will know how would it look like if you graph this X and Y pair of data. So look that this is at the temperature that is placed in here. So you have this particular curve for your benzene and not benzene, but rather pentane and hexane. Okay?
Miss, excuse me, miss.
Okay, wala naman siya
Wala
gamit.
siya gamit.
Thank you. Okay, so we'll just make this bigger. So this is the table that I was referring to. Now, if you are going to graph the pair of X and Y values in the table, this would be the curve that you will be producing. You just simply connect the endpoints of this curve by a 45-degree line. You have this. Graphically, you can determine the minimum number of stages like this. This is your XD. You start with XD, which is 90% pentane. Let me check. Yes, it's 90% pentane. Your bottoms liquid is 90% hexane. So meaning the pentane there is 10%. So you're using the 10% here. 10 and 90. So you do your steps in here and more or less based on this particular graphical approach of determining N minimum, you have 4. You have 1, 2, 3, 4. This is your minimum number of stages. Okay, that's it. Now, how about if you're going to determine it analytically, the minimum number of stages? Of course, you're going to use Finsky's equation. Now, what is this Finsky's equation? Let me just scroll up. So if you're going to use Finsky's equation, this was shown to you also. This is Finsky's equation, but it's too small. Let me try to have this projected if you can see. Can you see, class, if it's projected?
Yes, Miss.
Okay. So your Finsky's equation uses the XD and the X sub W, or the X sub B, the bottom's liquid mole fraction, all in terms of the lower boiling point component. So given in the problem is 0.9 for XD, and you are to subtract the 0.9 in the problem, which is that referring to pentane, so that you'll get the 10% hexane. Is it hexane? 90% hexane, 10% pentane. So you'll get the 10% of pentane in the bottom's liquid. So you just substitute it in here. Now the question is, how do you get this geometric mean of the average volatilities of the overhead vapor and that of the bottom's liquid? So you have here alpha D and alpha B. I hope you can see that. Alpha D for the overhead vapor and alpha B for that of the bottom's liquid. You take the geometric mean of that. You take the product and get the square root of the product. How do you then determine this? Because in here you could see that it's still not placed in, referring to the value. I'll just escape class and go back to the slides because I'm sure you won't be able to see. So determining the alpha requires you the mole fraction in the liquid and in the vapor phases of the distillate and that of the bottom's liquid. Okay. For your distillate, it is given that you have 90% N pentane. Okay. Go back ko ha, dali lang. Your distillate has 90 mole percent pentane. Now you're going to, supposed to be class, you're going to get the equilibrium, the equivalent equilibrium mole fraction in the liquid phase for this particular mole fraction in the gas phase. That's how it's going to be. It's a pair. What is the equivalent equilibrium mole fraction in the liquid phase for the given mole fraction in the vapor? Now, if you're going to look at the data in here that you have, you look for the 0.9, it's nowhere to be found because the closest value that you have, allow me to project. The closest value that you have to 0.9 is this class, the 0.9317. So we can use this one because we don't have the actual 0.9 value. Now, you may suggest to me that, Miss Ali, we can interpolate. Actually, we don't interpolate because we don't have a line. So we use only interpolation if we have a linear relationship between our data. Our y and x data is not linear. XY data rather is not linear. So you just choose the nearest to 0.9 that you have in here. So in that case, that would be this one, the nearest to 0.9. And you read from this particular table the equilibrium concentration in the liquid phase paired with it, and that's 0.75. Now, what will you do with this particular value? So you go back, so record this 0.90317 and 0.75. You go back to the formula given by Finsky here, and substitute the value for y, which is 0.9032. You don't place 0.9 because we don't have it in our data. And the equilibrium mole fraction equivalent in the liquid phase, which is 0.7. Okay? Now, you use the same value in here in the denominator. This is your formula in determining the alpha D. Okay? The relative volatility of your component pentane in the overhead vapor, which is converted into the distillate. This is for alpha D. What about for alpha B? If you're using the distillate mole fraction in the alpha D, you will use the mole fraction of the bottom's liquid in the alpha B. So this time, you'll be using the X sub 1. Okay, I'm going to encircle it. You're going to use the X sub 1 of your bottom's liquid, which is actually 1 minus 0.9, because you have 90% hexane in your bottom's liquid in the given. So 10% must be your pentane. So this is the 10% that you have. Just like the way you did it here for this value, closest value of y in the table, you get its paired x. Now this one, this is for x. You look for its paired y. Where will you look for it? You're going to look for it in the table of the data, the equilibrium data that was provided in the problem. So in here, make this bigger so you could see. Hope you can see. You look for the 0.1x. So this is the one. This is your 0.1x. The mole fraction in the vapor equivalent to this mole fraction in the liquid is 0.23699. Okay? So let me clear it because it will be shown on the next. So with that, you go back here and substitute 0.23 and 0.1. You have your 0.23 and 0.1. The two alphas, you will multiply and get the square root of the product of. Then go back to the formula that we have here, this one, and substitute. It will give you the minimum number of stages, which is 4.1. If you compare this value taken from Finsky's equation and from the one that we had based on the graph, more or less they are comparable. But of the two, of course, this one is more accurate, the one given by Finsky. Now this one will be dependent on how well you draw by hand the best fit curve on your data points, X and Y, coming from this table here. You don't necessarily pass to all the points that you have in here, but just like making a best fit line on a particular set of data, you're going to draw by hand the best fit curve that you can draw out of that pair of X and Y data. So this is the graphical way of determining the minimum number of stages. This is the analytical way of finding it using Finsky's equation. Now, do you have any question? Okay, if there aren't any question, for example, class, just as an example, in this problem, you're given this. What if you're not given this? You're just given this one. How will you find the pair of data that you will use in here for the alpha D and the alpha B? Let's say you have already you have the exact value of y sub n, which is actually your y sub D, equivalent also to x sub D. You are to determine the equilibrium mole fraction of that in the liquid phase, or the liquid phase mole fraction in equilibrium with this concentration in the gas phase. So how will you find that if you don't have this one? You're given this. Let's say sulion ta. Amo ni give hindi ni. So how will you find the values, or where will you get the values that you will place here in Finsky's equation for the alphas? Anyone? In here, you're provided with the data. So you can choose from the data there and just read the equivalent mole fraction in equilibrium with the mole fraction that you have been given. But if it's this one, what will you do? What will you do, Johan?
Miss,
What will you use the coordinates? How will I use the coordinates, Drexel? Or what will you do, Johan? So that you will have the pair of x and y, you will substitute for alpha D and alpha B.
estimate, Miss.
Estimate. Where will you base the estimate?
Sa coordinates, Miss.
Where will you get the coordinates? Because this is not given. This one is not given. You're given this. So where will you get it? I'm just giving a different scenario, checking whether you would know what to do. In this problem, you're given this. So the problem gave you two ways of determining the minimum number of stages. The first one is this. This is the easiest, the graphical. The second one is using the Pinsky's equation. So my question now, what if the problem is not giving you this table? The problem gave you this. What will you substitute here for the pair of x and y value in the alpha D and the alpha B formula? So you say you're going to estimate. Where will the estimate be based? You say you will base it on the coordinates. Where will I get the coordinates? The intersections on 45-degree line. Miss, you don't need the intersection of the 45-degree line. Don't need that. Where will you get it? Johan, would you know? Or Albert Villarosa? I have two answers in the chat box. Some more fraction, miss. Sa curve, miss. Hi, salamat. Sa curve. Correct. Very good, Jericho. You're going to get it from the curve. Isn't this the curve? This is the curve. Now, if the problem says that you have a distillate which is 0.9, allow me to project this. Let's see if you can see. And I will annotate. If it's 0.9 for the distillate is vapor, right? Distillate is vapor. So you go here, oh. Go there. Go to your curve. That's it. You said this is the point that it's going to intersect the curve. Read here the x. This is your xd, or rather in the formula, so that you won't get mixed up. In the formula, this is xn. This is xn, and this is your yn. Even better because you actually base it on the curve. The curve in the first place gives you the relationship between x and y. The curve is from this x and y. So this is it. In the bottom's liquid, it's liquid, right? So this is your x sub 1 based on Finsky's equation. You go up until you reach the curve. Read here your y sub 1. That's it. This is the pair of values you will substitute for your alphas in your Finsky's equation. Okay, class? So please train your mind to always think outside of the box. Don't box your thinking na amula na siya permit. What if? You always go, what if? When you study, why is it like this? What if the given is not this? It's this. What will I do? Okay, there's somebody right. Miss, excuse, wala ka santo ang pag-annotate mo sa graph. Wala ka santo. What do you mean, Via? Wala ka santo?
Wala na siguro, miss. Naka-zoom, miss.
Away siya nag-zoom. Sige, kay gamay karon iha. Sige, gamay yun ta. Oh, okay ha. We'll go back again to our discussion. Wala siya nagsanto because in me, I'm already having it projected. So, annotate again. You have here your YD. You want the XD. This is the 0.9. Go here. Read. This is your XD in Pinski's equation. Pinski's equation requires you the Y1 together with the X1, the bottom's liquid mole fraction. You go up until you reach here. So this is your 0.1, this one. And then you have this, Y1. So the pair of values you have will be the values that you will place in your formula. Okay na, Via?
Yes, miss. Thank you.
Sige. When you study, always think of the whys, what ifs. That will aid in your complete understanding of the principles and the concept. Now, I have Isa here, my student before. This one, we don't even discuss in class then, face-to-face. I only discuss to them graphical approach. I tell them, you study on your own what's the theoretical way of finding the, or the analytical way of finding the theoretical number of stages. Now, she may be happy because she's in this online class because everything is taught already. Okay? Do you have any questions? So that's it. You find the minimum number of stages from there. But we're not done. But before we go to the minimum reflux ratio, do you have any questions? Okay, there's none. So we still need to determine the minimum reflux ratio. I'll go up. Graphically, class, you determine the minimum reflux ratio based on the X prime and Y prime. What is the X prime and the Y prime? Those are the coordinates of the pinch point. This is your pinch point. The point, I will extend the feed line here. The point where your feed line crosses the equilibrium curve. So you have here Y prime and you have, sorry. Specifically, this is where your Y prime is. That's your Y prime. And this is your X prime. Actually, your X prime is your mole fraction in the feed. This is your X prime. When you have this, if you recall, somebody can recall the formula in determining the minimum reflux ratio using the X prime and the Y prime. Can you recall? We discussed that last week. So we have minimum reflux ratio.
Ano miss, x sub d minus y prime over x sub d minus x prime.
The Excel, so that would be x sub d minus y prime, x sub d minus x prime. Right? So from here, from that formula, you'll be able to get the minimum reflux ratio. Okay, class, if it's the scenario that I gave you a while ago. A scenario wherein you are provided with a curve or you're provided with the equilibrium data and you plot the curve, you can readily get the X prime and the Y prime based on the intersection of your feed line on the equilibrium curve. And by the way, make this blue. This is your, change that. This is your feed line. Will extend. The entire thing here is your feed line. Why is it vertical? Q is equal to 1. Your feed is saturated liquid. Now you have to be very observant as to the way things are being emphasized or specified in the problem. Okay, it's vertical because your Q is equal to 1 and it's a saturated liquid. Now I will erase my markings here. I'd like to go back on the problem to point out that phrase. It says here, the feed is saturated liquid. This may not be so trivial to you, but when you solve distillation problem, this phrase is very important. The one that describes your feed. It's a saturated liquid. So it tells you right away that your Q is equal to 1. If your Q is equal to 1, it's vertical and plotted right on the XF. Okay? Okay, so we'll have this here. So going back to that, you have the X prime, Y prime. And this is the formula that I have shown to you a while ago. So this is your minimum reflux ratio. Now the other way of finding the minimum reflux ratio is the one that is totally analytical. This one. You have to pass here, determine the theta, substitute the Q in here, and then you have to substitute the theta in here and find the minimum reflux. So that's an alternative. The graphical approach is an alternative of finding the minimum reflux ratio. Okay? Do you have any questions? There's none? Okay, so we'll have a 5-minute break, class. My time, or 6 minutes, make it 6. My time is 1:34. We'll have a 6-minute break. Just don't leave Zoom. Come back at 1:40. Okay? We will continue with the rest of what's in here for us this afternoon in this second half of the slides. Okay, we will continue where we ended. So we go now to special cases of rectification. So in these special cases of rectification, class, there's no need anymore to have all the operating lines in your equilibrium curve. You may need in some cases only 2 of the operating lines, or you may have an added operating line in the case of distillation with side stream. So we're going to look into each of these special cases of rectification. You can read this in your handbook, but specifically, Giancook is also simplified the manner of explaining the special cases of rectification in his book. Now, we have of the cases here, the first one, the enriching column distillation. From the term enriching column distillation, we only have the top part of the column. We don't have the stripping section of the column. In this case, your feed enters the bottom of the tower as vapor. So take note, your feed cannot be liquid, cannot be a mixture of liquid and vapor. The feed is in the state which is vapor as it's fed at the bottom of your column. Distillate is more rich in the volatile component. Bottom's product is comparable to the feed in terms of composition, but may vary but slightly or be slightly leaner in the volatile components. So most of the time, your bottom's liquid in terms of composition is similar to your feed. However, if you're going to compare the composition of the leaner component, meaning the more volatile component present in the feed, sometimes the bottom's liquid has less of that than that of the feed. But oftentimes, they have the same composition. Now, if feed is saturated vapor, we say that your feed now, in this particular scenario, is comparable to V sub N. This V sub N class, if you recall, is the vapor coming from the reboiler. Now, it's the vapor produced by the reboiler when it's returned into the column as vapor. Actually, originally, it's the liquid that goes down into the column, and your reboiler turns it into vapor and returns it into the column, back into the column. Majority, however, of this collected liquid is withdrawn as the bottom's liquid. So in this scenario, since your feed is vapor, then we look at it just like that particular vapor coming from the reboiler, and it's represented by V sub n. Now, the enriching line and the Q line equation in this scenario holds. So meaning, if you do graphical approach, the manner of plotting the enriching section operating line and the feed line is similar when your column is complete with the stripping section. Now, how does it look like? It's something like this, okay? So your feed in this case is just vapor introduced at the column bottom, or at the bottom of the column. Now, your vapor feed is labeled as V sub n in this case, just like the vapor coming from the reboiler, as I have mentioned also. You still have reflux being the part of the vapor that was condensed into the liquid returned back into your column. Majority is withdrawn as your final product, which is the distillate. This is for your enriching section or enriching column distillation. There is no stripping section in this case. Now, if we have enriching section or enriching column distillation, we also have what we call the wait class ha. How come I jumped here? Okay, I'm sorry. I jumped there. It should be sige na lang. So we have here the enriching column distillation. I'd like to go up because we skipped the stripping column distillation. So if we have the enriching column distillation, we also have the stripping column distillation. This time, class, we don't have the enriching section naman. Kaya na wala the stripping section, subong ang wala ang enriching section. So feed here is usually saturated liquid. So the opposite of the enriching column distillation, and is introduced at the top of the stripping column. So enriching is at the bottom, stripping is at the top of the column, and the state of your feed is saturated liquid because it's liquid at its boiling point. Now your overhead product V sub D is the vapor rising from the top plate which goes to the condenser, in this case with no reflux. So W, the bottom's product, is rich in the non-volatile component, just like you have the usual distilling column. Here, the column operates as a stripping tower with the vapor removing the more volatile component from the liquid as it flows down. So your liquid feed, specifically your saturated liquid feed that is introduced on top of this stripping column distillation, is flowing countercurrent the vapor that goes up. So in the process, the vapor separates the more volatile component that is present in your saturated liquid feed and then leaves the column. All the vapor is being condensed and there's no reflux in this case. Okay, now this could be found in this section of your handbook, figure 13-2, letter D. Now this is your stripping column distillation. So the exact opposite of the enriching column distillation. Feed, which is saturated liquid, is introduced on top, and this is your VD.
Excuse me, miss.
Yes. Yes.
Miss.
Yes.
Excuse me, miss.
Yes.
Ga-choppy ka, miss.
Oh, that's my connection. Siguro ay na. Can you hear me now? Hello? Can you hear me? Ay na? Hello? Can you see the stripping column distillation illustration?
Yes, Miss.
Okay, just let me know if I'm again choppy. Now you can see here that your liquid feed, the saturated liquid feed, is introduced on top of the column. It flows countercurrent to the vapor that goes up. In the process, the vapor takes away the more volatile component in your feed as it goes up. Now all this vapor is introduced into the condenser, and there's no reflux liquid returned into the column. All of the vapors are condensed and removed from the column as saturated liquid after it has passed through the condenser. So this is your stripping column distillation. It does not have the enriching section, just like the way I've discussed it with the enriching column distillation, which does not have the stripping section. If you're going to draw your this is where we are now. If you're going to draw the operating lines in this case, since your feed is saturated liquid, it's vertical. Okay, I can see that my internet is really unstable because I have here a notification that it's unstable. Is it okay now? Is it okay now? Can you hear me now, class?
Choppy, good gapon, Miss.
I think DSL has really some fiber na galing kami dire. I don't know why it's been like this. Okay, I will just continue, ha? Sige. So, this is your saturated liquid line, your feed line, which is saturated liquid. It's drawn right on the 45-degree line. It's vertical because Q is equal to 1. And you start off with the mole fraction of the feed in here. Now, when you draw your stripping section operating line, this line, you also start with the X sub W. That's the mole fraction of the more volatile component in the bottom's liquid. So you place that point in here. And based on the mole fraction of the vapor, or mole fraction of the more volatile component in the vapor, you're going to project that particular value right on the vertical line that you have drawn to represent your feed line. So your YD, which is the mole fraction of the more volatile component in the vapor, which is also equal to the mole fraction of the more volatile component in the distillate, will be projected from the vertical axis here horizontally on this vertical line, which is your feed line. Now, at this particular point where it crosses your feed line, you will connect to the X sub W, which you have placed right on the 45-degree line. So this is where your stripping column, or should I say the stripping section operating line should be drawn between these 2 points, X sub W and the projection of YD on the Q line. Start off drawing your stages on the YD here, or your steps, okay? And your theoretical number of stages, in this case for the stripping column distillation, would be the number of stages that you have here also minus 1 because of the presence of the reboiler in here. So you have to subtract 1, just like the way you do with the entire column having the sections, the 2 sections, the enriching section and the stripping section. So this is how we interpret a stripping column distillation. Feed is saturated liquid introduced on top. There's no reflux liquid that is returned into your column, and there is no enriching section. Okay? So that's our stripping column distillation. So I should have started with that before I went to the enriching column distillation. Okay, hindi siya maintindihan. Um, I will stop here, class. We will reconnect. I'll stop here. I'll stop sharing. I'll try to reconnect.